It is my pleasure to introduce the third Flamingo webinar speaker, Professor Dr. Janis Locs, who will give a 45-minute talk about the challenges of the laboratory synthesis of bone-like structures. The audience is asked to write your questions in the chat or raise your hand after the talk. Professor Janis Locs is a director of Institute of General Chemical Engineering at Riga Technical University and leading researcher at the Riga Biomaterials Innovations and Development Center. His main competencies are synthesis investigations of composites and calcium phosphate-based biomaterials for bone regeneration. Janis, we first met approximately 10 years ago, I think, as partners in cost action from nano to macro biomaterials and applications to stem cells, regenerative orthopedics, and dental medicine, Amabio, remember? How the cost actions affected your professional networking in general? How can you comment this?
Actually, it's the cost actions affected a lot. And actually, the webinar is a part of the Flamin-go project. We are both involved, and also if to link together my connections I got in cost actions, all of them came together, and finally also the Flamin-go came out. So I would say that it affected really a lot. I met a lot of people, and it's a really nice activity, and I always recommend to all of my group members to participate and to find the new connections, new ideas, and of course, then later the project comes and then things come.
Thank you. And now, please let us know about the puzzle of bone synthesis in laboratory. The floor is yours.
Yeah, thank you very much. So, share my screen. I guess you see it, right? Yeah. So this webinar is a part of a project from the Horizon 2020, from pathobiology to synovium on chip, driving rheumatoid arthritis to the precision medicine goal. And for myself, being a material scientist by my education and with some knowledge in physics and chemistry, but in general material science, in this presentation, I want you to show my vision and the way how we in our lab and also the scientists, the researchers around the world are dealing to produce the bone. And that's why I also made a little bit the title of presentation on the puzzle of bone synthesis in laboratory, meaning that how we are trying to put the puzzle together to really to get at some point, of course not yet, but to get to the really bone synthesis in the lab. And at the very beginning, as already was introduced by Sasha Novak, so I'm from Riga Technical University and Riga Biomaterials Innovation and Development Center, and from Latvia. And for those who doesn't know, so Latvia is here. As all of the countries said, we are in the middle of the Europe. So wherever you go in Europe, you are in the middle of the Europe. And we have a very nice campus for our university. And also I have, of course, a really nice team of young students, PhDs and postdocs, researchers that we always are trying to get fun. And also here, this is one of the young researcher nights where we show to the young students the miracles of science, and we also want them to be involved in the research. So now at the very beginning, I will tell a little bit about tasks of our group in the Flamin-go project, and currently we are involved in the work package 4, which is the work with the osteochondral unit, meaning that the project itself is designed to develop the chip, organ on chip for the osteochondral unit. And as the joint is quite complicated, also the chip consists of several parts, and all part actually is from all of those parts is really just the bone part, where we together with the EO Foundation, EO Research Institute from Davos, We are working on development of this small part, which here in the image looks quite big, but in reality it's going to be just a few millimeters by a few millimeters big, in order to mimic the bone part of this joint. And then, as I mentioned, that's I want to look on the bone as a material scientist, and let's say during this my presentation, so this 40 minutes, let's forget about the biology. Yeah, so let's just look on the bone as it is from the materials side of view. So what we see that in micro scale, so the bone can be from few millimeters in size, somewhere in your head, in the middle layer, and ending up with the tens of centimeters in your legs. And then if we look further, we have two parts of the bone. So we have a denser part and a more porous part. And also the porous part is, again, quite interconnected porosity with some specific range of pore size, which is about 200 microns, with some pores bigger, smaller, but that's the average range. And then if you look more closer to the bone, that we see that it's built up from the hierarchical structures, where some of those structures ends up with a lamellas, and then finally it's actually the composite, which is made up from the collagen and hydroxyapatite crystals. And as we see here, which is quite well characterized, that the crystals are plate-like structure. So the crystals are about 50 nanometers in length, 2 to 3 nanometers in thick, and 25 nanometers in wide. And just in order for you to understand that the size of this crystal is about 1/10 of the 10,000 times of the diameter of your hair that you have in your head. So that means that the crystals are really, really, really small. And now let's look on the composition from a material point of view. So we forget all the cells, we forgot the blood vessels, we forgot the nerves. So what we have a composite of from the inorganic phase, which is built up from the hydroxyapatite. And what is very important, the amount of the hydroxyapatite is really high. It's about 78%. And then we also have organic matrix, and that's the collagen, about 22, and only about 8% of water. So this actually, the combination is the one that explains why do we have these kind of mechanical properties. So that let's say the easiest for us to understand is the compressive strengths, 130 to 200 megapascals for cortical bone. And that means about 2,000 kilos per square centimeter. So that's, if you imagine the one car, which is a normal car, to put on the 1 centimeter by 1 centimeter area, or let's say on a tip of your finger, that's the pressure what the bone can withstand. And this came out actually from this unique combination of the mineral phase that gives the mechanical properties, and also the collagen, the organic phase, that gives the rigidity. Okay, so the task is clear. We need to have some part of inorganic, some part of organic, and at the same time, the inorganic should be quite specific in the size. And now the formula looks quite, the chemical formula looks quite complicated, but actually it's quite easy. So we have one source from the calcium, we have another source from the phosphates, and we do the reaction at the proper conditions, and we can achieve, or we can synthesize the hydroxyapatite or the mineral phase of from our bones. But then as we start to do it, there is also options to choose the calcium source. And we did it, tried in one of our research, a few of them. And here are just some example. So all of them are the calcium hydroxides. One of them are obtained from the eggshells, from snail shells, or commercially purchased from the as a chemical reagent. And as we do the first synthesis, first reaction from the calcium oxide in a reaction with water, we get calcium hydroxide. And as you see, that's the morphology of theoretically is the same chemical compound is really, really different. And that makes us already an assumption that there is something more in detail there. So there is something behind it. Of course, as seeing that, taking into account the reaction, anyway, it will dissolve to form the hydroxyapatite. We don't care much of that. And we do the synthesis. So here you can see on the left side, hydroxyapatite synthesized from several sources, from the eggshells, snail shells, and also 2 commercial calcium oxides. All of them look the same. The nanoparticles are needle-shaped, about 20 to 50 nanometers in diameter and about 200 nanometers in length. No big difference. But then, as we aim to get some mechanical properties to the material, so the first thing that everyone was doing for, and is still doing for many years, is the sintering. And as we do the sintering of those calcium phosphates, hydroxyapatites, we do all of them at the same conditions, 1100 degrees for 1 hour. And what we find out that there is a really big difference in the microstructure. And now the question comes, why? Why is this huge difference? And the answer is pretty simple, that actually in the raw materials, which I showed you before, the eggshells, snail shells, or even the commercial ones, they are never pure. Or let's say, if you want to get a really pure one, then you have to pay a lot of money for that. But from the normal sources, they are not pure. And also, at the same time, the hydroxyapatite in all bones, it's not pure as was shown in the formula before. So there are always different ions in the side, like strontium, magnesium, and even we have cadmium and zinc, etc. in our bodies. And those metallic ions are in small quantities. At the same time, they have biological properties in our body, and at the same time, they do influence the sintering properties of the ceramics. So that means that we should really take care of what raw sources, what raw materials we use in order to obtain the desired properties for our materials. So moving further, finding the proper way how to shape or how to shape those nanoparticles, we ended up with one very nice technique to sinter porous ceramics made of hydroxyapatite. The porosity is good, close to the bone one, and also the pore size is quite well. But what we recognized is that, yeah, we have a macrostructure. We can make quite big pieces of the material. We have more or less reasonable mechanical properties. Of course, they are not even close to the bone. If for the compression for the bone, there were 200 megapascals. So we are at least 4 or 5 times below. So meaning about 40, 50 megapascals. But that is at least something. And the biggest problem is that we lose, during the sintering, we lose the nanostructure. And we don't have the organic phase. So here, in this case, after the sintering, is really the ceramic alone. So the question: do we mimic the nature? And then starting to look on what's again back on what's in the nature we have. Okay, we have in our bones we have hydroxyapatite nanoparticles again. So this is the size range. And there is one specific parameter that can be measured for all of the nanoparticles, is the specific surface area, which is really proportional to the particle size of the material. As the particles get smaller, the bigger is the specific surface size, surface area. And also this specific surface is later related to absorption and desorption of the proteins and bioactive molecules in a body, and that is very important. So, and now if you look for the commercial or for synthetic calcium phosphates, like I showed you in the previous slides, what we see that the particle size is really huge, and also the specific surface area goes really, really low. And this gave us the understanding that the traditional sintering techniques that are used in the labs and also in the factories are not really the best options to mimic the bone or to produce the bone in the lab. And then we started to look a little bit in the nature. So what happens in the nature? A few years ago, let's say almost 12 years ago, scientists, Mohammed et al., they found out in the zebrafish that there are some small particles which are calcium phosphates, but they are not crystalline, as we do usually the synthesis of hydroxyapatite. They are amorphous. And this is a X-ray diffraction diffractogram that shows the amorphous states. And here are also the size of the particles that they usually are. And this made us aware that, why do we work with the hydroxyapatite? Let's try to work with the amorphous calcium phosphates. And then looking also a little bit later, so what are the amorphous calcium phosphates? So these are very, very small calcium phosphates clusters that are then shaped or organized in the amorphous calcium phosphate particles. And and actually recently, a few years ago, there were discovery, or let's say explaining of how does the hydroxyapatite in the bones are formed. So there are some osteoblasts that secretes the intracellular vehicles. They transport the collagen, and then the amorphous calcium phosphate particles are deposited. And then with the time, the amorphous calcium phosphate particles forms the hydroxyapatite crystals. And as you see here, that the amorphous particles are usually spherical, but the hydroxyapatite finally is really long, tiny, long plate-like particles. So now it's the next question. We got a really nice idea. So let's do what? We do the synthesis of amorphous calcium phosphates. And if we put them in a bone, so what should happen? The amorphous calcium phosphate will partially dissolute and also recrystallize. And we will have, we call it that we have the hydroxyapatite synthesis in vivo. So meaning that we could provide to the body, to the defects, amorphous calcium phosphate, and then later it would be synthesized in vivo. And then we faced another theory, which says from Boiler and Coulter that actually there is probably another way how it is formed, that at first there is the octocalcium phosphate particles, and then the octocalcium phosphate particles forms into the hydroxyapatite. And that way, and this is the explanation of why does the hydroxyapatite also has this plate-like structure. And we have done also this, so to synthesize the octocalcium phosphate. And let's, and now we just move forward to understand which of those materials would be the best. And as a next step, we started to look on the synthesis of amorphous calcium phosphate. So there are several methods in the field. One of them, which is called double decomposition, is the most popular, and it's relatively very simple. So where you have, in one glass you have calcium source, in other glass you have phosphate source. You just mix them together and you get the amorphous calcium phosphate. But there are many questions in order to get the proper product. So the calcium phosphorus ratio, meaning how much of each reagent to take, what should be the temperature of the synthesis, what should be the pH of the synthesis, and finally, how do we dry it? So how long and how much time do we have? As those amorphous calcium phosphate particles are not stable, and they at some point start to crystallize and form the hydroxyapatite already here in the synthesis media, which we do not want to allow. And in the parallel, we thought that it's from one point, it's good method, but within this method, there is always problems with the control of the pH, and we developed our own methods where we have the solution, acidic solution with a necessary amount of calcium and phosphate ions already in the solution. And as we rapidly increase the pH of the solution, we have the precipitation of the amorphous calcium phosphates. And now let's just compare what do we have for both. So do we mimic the nature so far? On the left side, again, is the size and specifics of the biological appetite. And on the right side is the results, the best results, let's say, what we got with the double decomposition method. And as you see, the particle size could be in range, but as the hydroxyapatite is very thin, also the specific surface area is still far, far away from the natural one. And then we move to the another technique where we increase the pH. And here we found out that yes, it is possible, depending on the temperature, depending on the speed, how fast do we increase the pH, we can ensure that the precipitation of amorphous calcium phosphate particles with the specific surface area in the range that of the natural calcium phosphates. And now we are being lucky, having the nice powder in the bottle. And there is a next question. Yeah, okay, we have it. Now we have to consolidate somehow, that we have to make the material itself that could be or could behave like a bone. So meaning that we have to make an object from the nanoparticles of the size of 14 to meters. And looking a little bit in the theory and literature, so conventional sintering that is used for hydroxyapatite, we cannot use it because of it. There is a phase transitions, and again we will get back to the first results where we have a huge piece of ceramic, and we do not preserve the nanostructures. And with the amorphous calcium phosphates, we found out that there is also in the literature a low temperature spark plasma sintering where they achieved quite a little bit densification of the materials. And then moving forward, we found out that there is also reports that it is possible to apply high pressure and also to sinter the nanoparticles at very, very low temperatures. So if for hydroxyapatite we would need in conventional sintering more than 1000 degrees. So here it happens already at 200 degrees. And that gave us the hint that probably this so-called cold sintering technique, or rather it's not cold, it occurs at 200 degrees, but anyway, it could be probably this adaptation of this technique could be used also for the sintering of amorphous calcium phosphates. Now, I just wanted to give you a little bit the introduction of how does the cold sintering works, meaning that we have the nanoparticles, we have the powders, and we also add a little bit of liquid phase, which usually is a water. And if we press strong enough particles together, we have a connection points of the particles, and the water around the particles works as a media, where the material from the particles dissolve and also precipitates back on the surface, in that way achieving the densification and formation of amorphous phase on the border area. So this seemed very, very interesting for us. And we made an effort to starting with the powder. And even we found out the way how we can do this at the room temperature. Of course, the pressures are quite high. So 1.5 megapascals, it is 150 bars, so meaning that's about 75,000 times bigger pressure that is the pressure in your tires of your bicycle. So the pressure is really, really high, and achieving these high pressures, we can go densify the material, go very high, and also consolidate, and at the same time we can preserve the nanostructure of the material that is really much closer to the bone than conventional sintering. So with this, we were satisfied, but the problem comes actually, what we don't see here is the porosity. So at this point, we know how to produce dense ones, materials, but we still have to introduce some porosity in here. So now if we look, do we mimic the nature? Not yet. So from one part, we can mimic that we have really nanoparticles in our composite, but we still lack the organic phase. So no organic phase at this point. And then together with the, let's say, with our partners from Poland, from the Institute of High Pressure Physics, we together developed one very nice technique. So in this case, it was nanohydroxyapatite. We found out the way how to make nice granules out of that. And at the same time, we introduced in this composition 20% of organic phase, or the polylactic acid, which is the biodegradable polymer. So in terms of that, trying to mimic at least from the combination of inorganic to organic phase, the composition of bone. So trying different kind of consolidation methods, again, applying the temperature and applying the pressure. We achieved really nice densification. And looking as a material scientist on the properties, so we have more or less the chemical composition that is going close to the bone. We have compression strengths, which is almost double that of the cortical bone, which is really, really amazing. So we were very lucky for that. But again, we are able to produce it dense, but not yet in the interconnected porosity. So this is one of the fields we should focus. We should work. So we have some ideas how to do it, but that's let's say, probably the task for some of the forthcoming projects. So, and then, so this is the information I can provide from our side. And then looking in the literature, there is a lot of 3D printing techniques coming up, where there is a lot of benefits with precise control over the porosity, meaning that you can program the 3D printing technique or the nozzle. You can print desired shape, desired porosity. And you can do, of course, also complex architectures. Later on, that can be used also for patient-specific implants. And somewhere later also with the bioprinting, meaning that you have the materials and also you add the cells to the material. So coming even closer to the composition of the bone. But there is still challenge of the inorganic phase composition and on mechanical properties of the scaffolds. So now we have, let's say, two parts in the development. So from one side, we are very close with the material chemical composition and also the mechanical properties to the bone, but we are lacking this degree of freedom to produce nice porous structure and desired shape. From the other side, we have this degree of freedom from the 3D printing to get the shape and the porosity, but in this case, the mechanical properties and also the composition, meaning the inorganic and organic phase ratio, is really, really far away from what is for the bone. And then I observed also one very quite recent development, where in the specific hydrogel baths, they added the cells and then they 3D printed in the volume the calcium phosphates, and they observed that the cells come on a surface of those calcium phosphates, and they form some kind of more like bone structure. So this is something I think is part of the future technology. So, but we just should find a way how we can add really high mechanical properties of these printed structures. So, and I'm slowly come to the conclusion. So what I found out, and it's very interesting that already in 1769, the calcium phosphates in the bone were discovered, and hundreds of years later, we still do the research for that. Since that time, in a Scopus, yesterday I found more than 20,000 research papers on the calcium phosphates in bone and tens of thousands of patents. But yeah, we are still in the way, and that's meaning that's the nature itself that's produce the bone in our bodies. It's not so easy to replicate, and we have to remember that it takes months and years actually for the bone to be created by the nature. But what we want to have to reproduce the same, maybe in a days or in a month in a lab, we still have to work a lot. And of course, somewhere in the future is that we will be able in a lab to produce real bone substitute with the mechanical properties and porosity characteristics, then later to add the cells, and to really mimic and synthesize the bone in a lab. And there is one very, very important aspect I didn't mention in my presentation, is also the biomechanics. As you see here is the example of the hip joint. And from all of those examples I showed you before, so they are isotropic, meaning that the materials we have produced so far, they are mainly, the properties in all the directions are the same, but in the nature, in our bodies, the loading on the bone for different points is different, and also the microstructure in the bone at the different sites is different to respond to the stresses from the muscles and from the joints that comes to the bone. And this is again additional degree of freedom to be added if we really want to produce the bone in a lab. And yeah, that's it. I want to thank my group. And here in this image, it's the shadow days in our lab, where we have the researchers, PhD students, postdocs, together with the school children, having fun. And this is also where we tell them or show them how do we work, what do we do, and we want them to be involved in the research, etc. And also, of course, the projects I presented from the results from, and also Flamin-go, and of course, Riga Technical University. And that's it for me for today.
Thank you, Janis. Thank you. I would like to start with a question. Can you spend a few more sentences about the connection or about the role of your group in Flamin-go project?
Yes, of course. So actually our group is involved in two activities. So one activity is in the formulation of the ink, of the bio ink for the creation of the organ-on-chip. Because of the idea of the Flamin-go is that to be able to produce hundreds of identical chips, meaning the small micro organs in a vessels, in order to test, for example, the drugs or some illnesses of the people, and that consists of several parts, several organs, and in our case. What we do, we work on an ink for the bone part of the chip, and together with the EO Foundation in Davos and Regenho and other partners, it's just one part. So then later the cells should be grown in there, and what we aim is also the blood vessels nearby. So it's going to be really complex structure to be built up in 4 years, and this is where we are going. So. I hope, let's say, we should do it, and we will do it, of course.
How far you are currently?
Yeah, so currently, at the end of the last year, we delivered the ink for the bone and for the cartilage part. And now currently there are last tests for the in vitro tests, meaning that the cell growth in those hydrogels are being tested, maybe some last fine-tuning of the compositions or viscosities. And actually the paper, also the research paper, started to be drafted at this point. So currently one of our postdocs is also in Davos in Switzerland, and they work really together with the Davos team. So let's say, it doesn't matter that we are two partners in different countries. In a way, it's much more efficient when they work together. And now Jana is there in Davos, and for half a year to work together to finalize the step to get really the part of cartilage and bone ready.
Great, thank you. Now I would like to ask the audience whether there is some question. You can either raise your hand or write a question into the chat. Is there any question? I cannot see any hands. So I will ask you something about what you mentioned, that the main issue now for your scaffolds is 3D printed scaffold is that it's not porous enough, or the porosity is not the proper one. Is it possibility maybe to use a 3D printing method and print two phases at the same time, like your ceramic ink and something which is water soluble, to print both of them and then dissolve the water soluble phase?
Yes, this is one of application, or let's say one of the solutions. It's in that case we call it sacrificial phase that can be dissolved. But what we face here is the technology itself. So the technology requires really high pressures.
For what? So the high pressure for what?
To consolidate the materials. So we have
no, I'm talking about 3D printing. So if you 3D print both, at the end you still have to densify it.
Yeah. At the end we have to densify. Mm-hmm. And then we have tried those things already with the two phases. Let's say to put some porogen inside. And then we face another problem, that if the porogen's elastic modulus doesn't fit the calcium phosphate, so we compress it, we have nice composites. And then as soon as we release the pressure, so the elastic one expands and it breaks up the structure. So there is it seems easy. We thought, okay, let's go. We could put some fibers inside and then we could dissolve those fibers, but it doesn't work the way we would like. Actually, we have some experiments done. We have achieved some first samples, but now we are really working on more results to get quite nice papers out in a coming years.
Okay, are there some other ideas in the audience how this issue could be solved? I know this is a big challenge for you, but still. Okay.
We have a field of young researchers.
Yeah.
Anyway, I think this is not the solution we can achieve or solve in 1 or 2 years. As I already mentioned, so it's hundreds of years it have taken to investigate the calcium phosphate, or let's say when they found out the first time that the calcium phosphate is in a bone, and only years ago, let's say a few hundred years later, they described really the mechanism, and that just shows this complexity which is there. And as more we know about how it is formed in nature, the more we can think about how we can replicate the same process also in our labs. And I always think that the processes that occurs in nature, they're the most effective, the most nature friendly, meaning that no toxic wastes or not really huge amounts of or energy use, because of our body really doesn't produce so much energy, so no high temperatures and etc. So I think it's still tens of years to go to have this solution.
Yeah, but as you said, a lot of work have been done already, but still there is no good solution. Is it possibly the reason for that separately biologists and material scientists are working on this area, and maybe there is not good collaboration between both, because maybe there is a way to replicate what nature does. But here you need collaboration of both, but biologists and material scientists, I guess.
Yes, for sure. This is a big problem, I would say, and this is why the projects like Flamin-go are out there, because for us, for material science, we have one view which I presented today, and the biologists have different views. So the biologists think that okay, we don't need these kind of huge amounts of inorganics, so we just take a hydrogel, put the cells inside, and let them do the work. Of course, that's another alternative, and that works. But so we have different views on that. So our aim is to have load bearing, let's say, meaning that if you have the implant, that you could load bear it already next day after the operation. But from the biologists, they want more really make the nature type. So, but I think that's the truth is somewhere in the middle, and there should be really a good cooperation, and it is already, and it should be more and more that they work together to solve the problem much more efficiently.
Okay. Thank you, Janis. Would you like maybe to add something at the end for the young generation, maybe?
Yes, of course.
Yeah, even younger, sorry.
Even younger. Okay. Yeah, thanks for that. Yeah, what I would like to say is that come to, so let's say, learn engineering sciences, learn medicine, learn biology, chemistry, physics. It's very, very interesting. And really the beauty comes out when you discover something. It's really good feelings, and especially if your discovery then later is used by someone else, even to move forward. So that's the part of the civilization. So this is how we got those computers, and this is how we have our phones, because of tens of years back, one guy decided to have, or a girl decided to have the silicon chip and to make a first transistor. So each of us should have to make our own inputs in the full cycle of development, and only this is the way. So one person is not a fighter. So we should fight together.
Thank you. Thank you for this and for the talk, interesting talk. And if there is no question and I cannot see any raised hand or question in the chat, then I would say again, thank you and goodbye. Have a nice day.
Thank you very much. Bye.